Hello everyone again, and welcome to this particular video where we're going to continue from where we stopped involving Herc reactions. And in this particular video we're going to look at a specific segment of the cyclic Herc reaction pathway, which is reductive elimination, and we're going to see alternate bases that will be used to actually give back inactive, or I would say Palladium, where it starts from, which is 14 electrons. So in here we're going to at least get a little brief intro into Herc reaction, which are the big ideas. Where one, we're going to start off with oxidative addition of an organic halide, and in this case here we'll have a halide attached while we have the organic path attached as well to a specific region of the palladium that already has its, I would say, two ligands attached to it. And then once the oxidative addition happens, then we introduce the other component, which involves a specific form of carbonmetallation, where we insert our olefin, and this olefin usually has the alkyl active electron donating region, where in this case we have a little bit of a pi interaction between that and the metal, and this leads to a formation of a sigma bond, and this sigma bond between this particular metal complex here actually leads to the specific point where we have a beta hydrogen, and this beta hydrogen performs a process called beta-hydride elimination, which then gives us our specific target product, which is shown by the dark blue product right there, and we see our active Alkene region right there. So this then leads us to regenerating our original specific catalyst that will be performing the next cycle of regeneration. So this regeneration path here is responsible, mainly called the reductive elimination of our palladium 0 catalyst coming from palladium 2. So in here we'll need a specific reagent, usually a base that is really quick at getting that proton out there and also a halide out of that particular complex to give that electron or lose that electron in that particular clump complex. So take note there that we're going in there from 16 electrons back to 14 electrons. So in this case here, to achieve this, we are going to change the oxidation number of palladium complex from 2 plus back to 0. Therefore, in this case, our palladium metal itself will be able to gain back that electrons due to the process called reduction. So in here we're going to focus on the base that is responsible for that, and that is our goal, and the diverse different bases that are responsible for this pathway. So let's look at the different bases that are required to regenerate our palladium 0. And one here is called the amine, and any form of amine will do a great job. In this case here we have trimethyl amine, and the other one here is called a phosphine. Another phosphine in here, they are also responsible as well for regenerating, and sometimes they can act as a ligand exchange process, or they can be used to actually activate our specific or get our palladium involved in the process. So this could also be a solvent as well in that particular solution. Now the next one here is called an alkene. We know different alkenes, many are used for that specific carbonmetallation, but this one here is an alkyl which is good at actually giving electrons out because it's a good electron donor. This could also be used as a base in a specific region within that specific type of cyclic Herc reaction, and that also leads us to our final one, which is called an organometallic. And an organometallic here is quite interesting in terms of its mechanism, and we're going to dive into the individual mechanisms that are actually responsible for this specific regeneration of our palladium 0. So first mechanism we're going to look at is involving amine. So in here we have an amine here, and this type of amine will be introduced to our specific palladium 2, and we know that because we have two X's attached which are both negatively charged. Therefore, in this case, due to a Ligan exchange, we actually have a form of an SN2 reaction where we have an amine lone pairs being donated to the palladium, while the good living group actually is one of the X, and this actually results in the positive charge complex that is noticed in this particular metal complex right there. And what will happen next is that since we have our X actually leaving this particular complex, we have the next step, which is the beta-hydride elimination. And in this case here, we have our beta hydrogen being used to actually remove that specific amine from that particular complex. Therefore, our hydrogen will be bonded, forming a sigma bond with palladium in the complex, and we have a good living group in here, which is our amine. Therefore, in here we have a complex with the hydrogen attached there, and then we have in this case we call it an imine in here. And this actually then leads us to the next step, which involves a reductive elimination, where we have the removal of our halide, where we have the hydrogen and the X actually coming together, while we have the regeneration of our palladium. So in here what we see here is we have our palladium which is regenerated, and if you look closely at the oxidation number in here, the palladium has an oxidation number of 0 compared to where we started from, where our palladium had the oxidation number to be 2. So this is one way by which we can be able to regenerate our palladium using an amine. Now the next step here is phosphine, and how with phosphine, or how is this different from amine? What we see here is that in this case we need two phosphines, and what phosphine does is that it performs a specific type of process with the palladium here. Since we noticed here the palladium to be in this case palladium 2, we actually perform a process called a Ligan exchange, and this Ligan exchange involves that we are not only going to have one phosphine but two phosphines, therefore generating a positive charge, and this actually leads an attraction to the lost OAC. So therefore this negative ion or anion here will be involved in a form of integration to the phosphorus in the phosphine that has a positive charge due to the attraction. Therefore we have the formation of this metal complex, and what we notice here is that since the AOC is also involved in the solvent system, either due to the presence of an counter ion base in there, or in this case could be a positive charge, this actually leads to a reductive elimination where we have another OAC involved, which has a negative charge involved in it, some kind of an SN2 like reaction, but then this leads to a cascade of movement of electrons that breaks off a couple of bonds where the double bond is reformed. Therefore this bond breaks and forms a double bond between the oxygen and the phosphorus, and then what happens next is that this bond breaks and it's actually forming a lone pair with palladium, where this bond here breaks to actually form a lone pair with the oxygen AC. Therefore, as a result, we are going to generate our side product, which is AC2O with the phosphine oxide, and finally we have our phosphine with palladium. And if you look closely at the palladium that is generated, we actually generate our palladium here to be oxidation number 0 coming from oxidation number positive 2. So this is another way by which, through this mechanism, that phosphine can be used to regenerate palladium in order for it to continue that same cycle of catalytic reaction. Now the next one, which is the third and final one, involves an alkene, and an alkene has something interesting here. It has pi bonds, and these pi bonds will form an interaction with a palladium, thereby causing a form of a migratory insertion. And what we see here is that this palladium, which has an oxidation number of positive 2 due to the 2 X's in here, which are all form of halogens. In this case, what happens is that we have a bond breakage, which leads to the formation of a sigma bond. Therefore, our pi bond here actually breaks to form a sigma bond with palladium. Therefore, in here we have our migratory insertion that leads to the formation of this type of single bonded carbons. So what we see here is that at the far end of the carbon bond, we actually have not only a hydrogen here, but also a halogen in there attached to that particular carbon. Therefore, what we see in that region is that due to the process called a beta-hydride elimination, this beta-hydride elimination leads a hydrogen, which is a beta hydrogen, to actually form a sigma bond with the palladium, while we have the breaking of our sigma bond between the carbon and the palladium to form a particular pi bond. Therefore, in this case, we are forming our form of an alkene halogen. Therefore, as a result, we actually generate our palladium, which still has an oxidation number to be positive 2. So therefore, by reductive elimination, we can then arrive at our final step, which leads to the formation of a halogen that is generated, and then we have the formation of our palladium, which now has an oxidation number, in this case, to be 0. Therefore, this is the third way by which we can regenerate palladium from palladium 2 to palladium 0. So since we have this taken care of, how about the last one? The last one involved an organometallic, and these organometallics, they are usually known to be called Grignard reagents, and this Grignard reagent comes in 3 forms in this particular type of Heck reactions: DIBALH, we have butyl lithium, and we have trialkyl aluminium. So therefore, in here, any one of these would take a specific short form, which is represented as RM, and we know that we're going to use 2 of RMs in order for we to actually perform this specific type of regeneration. So therefore, if we have our ligand in here, catalyst, which is in this case palladium, which has 2 X's, which are the 2 halogens, creating the oxidation number of palladium in there to be positive 2. Our first organometallic here comes in, and due to ligand exchange, we actually have the formation of not only 1 but 2 attachments of our R group to the palladium, thereby generating or releasing our metal with the X, 2 of them. So therefore, in this case, what happens is the formation of our groups attached to palladium, still having the oxidation number of palladium to be +2, while we have the release of our particular form of ionic compound that is generated, or salt that some people might call it. So this then leads us to the general reductive elimination, where in this case we have our R group, one of the 2, actually forming a new sigma bond or new carbon-carbon bond, while we have the breaking of our palladium with one of the R group bond to form a lone pair with the palladium. So therefore, in this case, we are generating a fresh alkane, and we actually release or regenerate our palladium, which has the oxidation number here to be 0 and coming from palladium, which has positive 2. So in conclusion, we are able to actually regenerate our palladium 0 from palladium 2 by the 4 ways. One is by the use of an amine, the second method is by the use of phosphine, and the two that are similar here is that we perform a Ligan exchange for both, and in that case we actually have the generation of our two going from positive 2 into 0 for palladium. And then the only thing here that is different going into the third way, which is by using an alkene, is through migratory insertion, and this is going to be important enough for we to actually generate a form of sigma bonds, and then from sigma bond we will generate a pi bond again with the addition of or incorporation of our halogen to that particular compound that is formed, and therefore this leads to a reductive elimination that leads to the regeneration of our palladium 0. However, this here, looking at the first and the third one, is different from the second one because the second one here doesn't have any form of beta-hydride elimination. And finally here we have the last form, which is the use of an organometallic, where in this case we don't have any form of beta-hydride elimination step, which is common with that of the phosphine method in there. So that's about it for this particular video. Hope you're able to understand the forms or different bases that are used to perform or regenerate our palladium 0 from palladium 2, and therefore restarting or kicking off that same cycle of Heck reactions. All the same, thanks for following me through this, truly appreciate it. See you on the next video. Please don't forget to subscribe, by that way we can talk more. Stay smart and believe in yourselves.